The last time had a little bit of issues with recording, so didn't do any exercises, but I hope that two main statements are clear, and the statements are saying that whatever you're trying to prove, first you test for one, and then you make a following statement. So the second part of it says, if works for K, whatever statement you're trying to prove works for K, then, and that's what I need to prove, whatever, actually, that's what's being proved. Then it works, same statement. It for the next element, which is K plus 1. Sometimes people wondering why this is true. Then it works. It seemed to be obvious, right? So if it works for next element, the next, which is K plus 1. In other words, if you start at the first element, and then if it works for first element, then it works for K plus 1, which is 1 plus 1, it's a second element. And if it works for second, then it works for plus 1 third element, and so forth and so forth. So it seemed to be pretty obvious, but they do prove this in later classes for math. Why don't I illustrate you this proof? Because that's a pure logical proof, and those people that may plan to do some math, I think will get a flavor of what you're gonna do in more abstract classes, the following algebra classes. So it's actually called number theory. That's where they do the proof of this statement. So it says, what if? So the key idea here, if A, then B is equivalent if you're gonna negate both. They say if not B, then not A. That's from logic. I'm not sure if you actually saw the logic, but it turns out if you negate both statements, then the then this implication, so-called, this arrow that said then, reflects. For example, we can take, say, if Alex is online today, then we have a class. If Alex is online, then we have a class. If we don't have a class, then Alex is not online. Don't have a class, Alex is not online. So you can think of various situations if then. So you can say, what if no class? Well, then it means Alex is not online, because if Alex is online, then we have class. So that's how this works. And that's where they actually, that's what they utilize to do proofs in math. So that's logical equivalence of two statements, turns out. So what they do is they say, what if this doesn't work? According to that process, they say, if this doesn't work, so how can I relate it with that one? Not working for hard time. I need to practice to write those words. Is this not working for k plus 1? So what we need to show then, not working for k, or for some less than k. So these two are given, and then we show that this is not working for k. So that's what the second part is. So how can I justify that? Well, turns out justification is as following. So you say we are given that statement works, right? So not work. So statement works. So if k is here, then k plus 1 is working. So what if it doesn't work for some element? Well, we can always find the previous, which is less than that. And then we say that from here, it must follow that. That's what's given to us. That's why we get a contradiction. In other words, not A. So if it doesn't work for B, then we get not A. And that's equivalent to show that if A, then B. So this is like structures from logic that people getting used to in the later classes, because one may say, Alex, what is that you just said? Well, if you are interested, you can think about this, because it's not obvious. It takes a while to try to understand this, but that's how they usually prove it. I know it's a little bit artificial, but well, that's the way they decided to prove things. So they started with various definitions and various theorems, like the one here in the upper left corner. And then they say we're producing this theoretical part, and that will enable us to prove various statements like we have for mathematical induction. And the idea of this statement is it works for all. See the key idea, maybe I wasn't clear on it. So the conditions here regard that statement is true for all numbers. So what they do is they say, what if it's not true for all numbers? Well, then we find a number for which it is not true, call it k plus 1. And then we have a contradiction, so because the works for previous, because that's the first number for which it doesn't work. So for previous works, it must work for that. So that's like the key idea in this proof. But anyways, I think if you don't plan to take more of mathematical classes in the university, you're probably never going to encounter these ideas. But in calculus class, we use this so-called contrapositive argument to prove things. And I think it's good that I give you a little flavor before you move to Calc 1, because some instructors, they well like to do proofs, and it's when they use so-called epsilon delta language and other things, and that's where some people get stumbled, and that's why sometimes it's not being covered. So anyways, I think I should move on, but the idea of proof is actually here throughout the entire section of mathematical induction. So, for example, we tried last time to look at the 3, right? Example 3 to do the proof. Remember, we wrote it for n equals to k, and then we also wrote what we need to prove for k plus 1. And then we produced from the k plus 1 case. And that's actually the one we did with example 1. And here is example 3 that is analogous, but it's involved, well, a little bit more algebra. So I think I will try one exercise here because they might be a little bit, well, too much involved in algebra. But I think it's good to see it sometime before taking some more mathematics, because lots of times they say use math induction, we get a proof, but then actually never do the proof, because proofs for math induction is always are always pretty much the same. So for example, if I try number 19, let me do one proof, number 19. Usually they are very straightforward, those proofs. Once you write down everything you need, then it comes out automatically. So let me share a little bit of room for you here and try exercise number 19. That's a section in mathematical induction 12.4. So let me 12.4. You can write down the straight symbols very easily, but this like section, those things. But anyways, we have number 19 that says if divisible by 2, what does it mean divisible by 2? Let's say, Alex, you can divide this by 2. Well, it means it's even number. You can approach it this way. N squared plus n is divisible by 2. So I can write this as, say, 2 times p. So what is divisible by 2 means? Well, numbers divisible by 2 are 2, 4, 8, right? You can divide this by 2, even numbers. So Alex, you forgot 6. Okay. 8, dot, dot, dot. So I can write them all as 2 times p, which is 2 times whatever whole number you can think of. Even integers, they could be negatives as well. So if this is n, so what do I need to prove? So I'm given that. What I need is to show that first condition of induction works. So it works for 1. So if n is equal to 1, then we have 1 plus 1, actually 1 squared plus 1. So why'd you write it? 1 squared plus 1? Well, if n is 1, I just plug it in. I see what this is. 2. Is that even? Yes. Divisible by 2. So second condition, if it works for, so if it works for n equal to k, so what does that mean? N equal to k. Well, just plug k here. So k squared plus k is even. Works means this is even, right? Because if it's even, yeah, I can divide it by 2. If it's not even, I cannot. So what do I need to prove? The key idea. Prove that works for k plus 1. Okay. Works for k plus 1. So the idea is just to write this down, and then you will see right away that it works. When is the final? 2 weeks from today. So it's in the syllabus. So we put, instead of n, k plus 1. So we put k plus 1 squared right? So what does it mean it works? It means it's even, right? So that's our goal. So just stick k plus 1 instead of n. It looks like I need some algebra to make sure that I show clearly that this is even, so 2 can be factored out. Okay, so let's try. K squared plus 2k plus 1, isn't it? When you multiply k plus 1 by k plus 1. Did you ever try to multiply k plus 1 by k plus 1 before? Just square first, square last, and twice their product. And there is still that k plus 1 left. So then what? Well, looks like I can put some like terms in here. And I should be careful when I put like terms because I already know that k squared plus another k, right, is already even. How do I know that? Well, it's given to us. It's here. So it works. So it is even. So this part I already know it's even. So what's left? Well, this guy left and these two left, right? So what left is 2k plus 2. Is that even? What do you think? That's what we need to show. Yes, it is even because it's 2 times k plus 1. I say is even as a factor of 2. Or we can say it's 2 times k, so it's even, plus number 2 is also even. 2 evens are even. Or I could say as 2 is a factor of that number. You can take out 2 if 2 is a factor, right? Like here, 2 is a factor, then it's even. This 2 is a factor, just factor. And that's it. So basically, all work was to write what we have, and we have given that part. For n equal to 1 usually is straightforward. And for k equal to k is also given that it works. What does given mean? Well, it works. We started the assumption works. And our goal is to prove that it works for k plus 1. So you write out what k plus 1 is and then look for what is given to you. Given is k squared plus k is already even. So I pulled out whatever we already have. And whatever is left over, I need to show was also even. So it is also even. So these kind of things I know that seem to be kind of offline in math, right? So I'm not gonna give you the final, so people wonder about final. That's great. The final is not gonna have this section on it, but I think it's good that you see it, because if you take more math, in fact, Calc 1, some instructors will use induction in the proofs. Again, in the case if they actually decide to do proofs, I know that some instructors don't like to do proofs, so it's up to them. So anyways. So I want to move on a little bit into something less advanced, I would say, in something that you actually see in statistics class. Because next section, let me go out of here. So in 2 weeks from today, in the 2 weeks, Monday next week, and then Monday week after next will be our last day. Of course, I'll be available on Zoom the other days after that as well, but I want to give you final on Monday. The reason is some people never make it and they have all kinds of excuses. They need more time and other stuff. I don't even want to get into that, so I just give final early, and if they want to have extra day or two, is fine with me. So not hurry and just make sure that I receive your work. Because if I give a final at the very, very last moment, the practice shows somebody has issues and forgets or whatever happens with internet, and I don't want to fail people because of this. Things happen, so I just give it earlier. I think it's easier to most people anyways. So let me go back to the textbook, and so that was a very good question about the final. Actually, it's great that you here, so we don't have much time left. So section 12.5 is so-called binomial theorem that we are using a special symbol for it called combinations. And this symbol combinations has been discussed in the next chapter, actually. So that's why I want to take a look at the next chapter. And then I will return to this last section of chapter 12 that deals with this symbol combination. So for some reason, they should have discussed that a little bit. See, that's symbol called combinations, heavily utilized here in so-called binomial theorem. And that's the last section of 12. So I plan to return back to it. It is not hard, it's pretty standard. There is only one formula. But to get to these combinations, we need to talk a little bit about permutations and combinations. So how we count various elements. And that's the idea that you see here. And I think that maybe I'll just concentrate on permutation and combinations. So, and I don't think that 13.1 is relevant to it. So I'll start with section 13.2. If we have time, maybe I'll return back to 13.1. It's actually a separate section. I don't know where they put it here. But 13.2 is a key section to the combinations, and that's exactly what they're heavily discussing in the section that I leave out for now. So what are those permutations and combinations? Well, first of all, there is a special symbol that they are utilizing that we already worked with, is called factorial. So they like to use that symbol here. So I want to take a look at that here. So for example, when you multiply numbers 5, 4, 2, and 1, remember we used to call it as a 5 with exclamation mark. It's exclaim factorial, and that's actually what it is, 5 factorial. So what they're talking about in this example. How many ways can you line up 5 people? So out of 5 people, you can choose for 5 positions in a line any one of these 5 and put in the first place, right? So you can select the first person, put it, say you're going to be first, or the second person, or the third, and so forth, or the last one. So there are 5 ways to put the first person in this line. And once you have selected the first person, for the next position, there'll be only 4 left, because the first position is already taken, and that person is gone. That person is in the first position. So for the next position, there are 1 less possibilities. There are 4 only. So you put the second person in line, and then the third position. Well, 2 are gone, so you no longer have those 2. You have only 3 to choose from, right? And you select another one. So you left with only 2 people. So there'll be only 2 choices for the next position. And finally, only 1 person just fills the rest, the last spot. So no selection, you just put the last person automatic. So people say it's 5 times 4 times 3 times 2 and times 1. And when they multiply these together, they get 120. And that's so-called number of permutations, number of ways to permute 5 people in those 5 spots. One may say it's not very clear how this works because it's really kind of tricky. So you can try to create, sometimes people have a tree diagram. So there is a first place and you have 5 people, say names A, B, and C. I'm not going to do it with 5. I'll just put 3 because 5 is too much. So in the first position, I can put either A or B or C. That's my first position, right? Then for the second position, I can put with first already being A, I can put either B on the second position or C, right? And then with the possibility where I have first person called B, then for the second position, it's either going to be A or C. You see how it comes out? So I actually put them on the position. So I show it not abstract way like we did before, but clearly show the arrangements that are possible. So possible arrangements are here. So if C is in the first position, it's either A or B. And then finally, the third position. And for the third position, I don't have any choice because I have only 3 people, A, B, and C. So if I already used A and B, then for the third position, I just put C. If I used A and C, then for the third position, I have B. And if that's a B and A, then I have C, right? Whatever is remaining, B and C, so the third person is A, and then 2 more. So there'll be C first, A second, then B is the third. And then C, B, then the last is A. So I just created all the permutations. In fact, if you start to count how many we have first, so it's like A, B, C. The second is A, C, B, B, A, C, and so forth. So it looks like you go along the branches of this tree and you see that for the first place you have 3. For the next place you have 2 choices. And for the last place you have 1 choice. So there are a total of 6 of them. Total is 6 if you list all these A, B, C, A, C, B, B, A, C. So that's the number of ways to permute 3 letters or 3 people on those positions in line. And of course, if there be a 4th person, then this structure will appear again with the first person like that, or if you put the first person, the other one, so there'll be, so it's lots of writing. That's why people don't try to write. In fact, 120 for 5 people will take you probably a good hour to try to produce, and that's something people don't want to do. But what people notice is that when you multiply, you just keep getting smaller and smaller and smaller by 1, and that's the idea of producing those permutations. So for example, if they look at permutations from 26 choose 3, so if they have 26 people, and if they want to select only 3 of them, say we select 3 people, and for the first person we have how many choices? Well, you can put any of these 26 people in the first position, right? And then once you put someone, you have left only with 25, and that's what's going to be for the next position. You can select any of these 25 people for the next. And finally, for the last is 24, because you're going to, again, use that person and be left with 1 less, so it was 24. So now you're choosing out of 24. And again, it goes end, and end means times, and that's how we produce this number, and that's a number of permutations that they're discussing here. And you can use a calculator. Actually, I'll show you how to produce that huge number that they have in here. So now they arrive in the formula. So the formula is the following. What you can do is you can look at 26 factorial So instead of multiplying these numbers, 25, 24, and stop at that point, you can go 26 factorial, which is actually gonna continue further on 25, 24, 23, 22, and all the way, remember, up to 1. So that's why people don't really like to put all of these numbers. It takes a while. So they put dot, 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 and then all the way to 1. But then they say it's not this product because we have only first 3. So we need to get rid of 23, 22, 21. So this denominator needs to contain those numbers, right? So they get canceled. So what I can do is I say I divide by 23 factorial, and turns out you produce it by taking 26 minus 3, because what you do is take 3 spots. So if there are 3 spots here that you need to fill with these 26 people, actually with 3 out of 26. So you go 26 minus 3. And that's exactly what they call as number of permutations from 26 people choose 3. And that's where this factorial stuff appears, because this tail that's following 24, so 23, 22, you want to get rid of it. You cut it out by taking this in denominator. So this is the formula that they have, and I try to justify it a little bit. And people usually use a calculator to work it out in statistics class, but I think the point of this whole section is to give you an idea of these permutations appearing. And this is very popular, actually. I can take a look at some exercises that deal with permutations. So how many arrangements you need? Let me say that here they give you first problems. They just ask you basically to use the formula. How about exercise number 31? Let me do a couple of problems and then I'll stop with permutations, because I think this is something that works for you to observe. And then on Wednesday, I'll do another part of this section, combination. And that's exactly what we need for that previous chapter, section 12.5, that I want to return to. So we'll just work with permutations. So 2-letter codes, they want to produce codes. So from letters A, B, C, and D. So from 4 letters, they want to choose 2. Right? And codes that I can choose could be AB, for example, AC, or BA. Would code AB going to be the same with BA? And the answer is no, not equal. Because if you enter code AB, or if you enter code BA, looks like this code is not going to work. So this is not going to be the case. If you go into not allowed to repeat letters, so permutations appear from 4 letters to select 2 when you cannot repeat those letters. In other words, if you used, let's say, letter A, since there are 4 of them from my code, you cannot use it again, so it's gone. So for the second letter, you have only 3 choices. And I can calculate this by taking 4 factorial on the top, right? The formula says take difference of these 4 and 2 on the bottom. So you could either do this intuitively or use the formula. And I try to use the formula and also do it intuitively to better show you what's going on. So 4 minus 2 is 2 factorial, right? Factorial stays. And what's 4 factorial? 4 times 3 times 2 times 1, right? So actually that 2 factorial is going to cancel. And we get only 4 times 3, which is equal to 12, right? 4 times 3. And this is 12. And nowadays you didn't really have to use the formula. You could have said, I have to choose 2, right, letters. So for the first selection, I have 4 choices. And for the second selection, and means times, I have only 3 choices, 1 less. So that's 4 times 3 is 12. But that's not what exercise 31 says. 31 is a little different. It says repeated letters are allowed. So 31 actually is saying you can repeat letters. See, so what was the difference? Well, for the first position, you have 4 choices, any of these letters. But for the second position, you again have 4 choices. In other words, if you selected A, it doesn't mean you cannot use it again. So you can use code as AA or BB, because in the case of permutations, repeating is not allowed. So you cannot use the same exact person 2 times and put in a line of 4, say, okay, Alex, you will be end first and last. Where do I stay? Do I stay in the first place or in the last place? It's not possible. Well, with letters, it is possible. You can use, say, or say A in the first and then A in the last, right? So if you use letters, you have plenty of letters. Or if you want to have plenty of Alexes, you can just clone Alex and get another Alex at the end. So that way it's going to be odd, but that'd be the case. So for exercise 31, it's actually going to be 16. Notice that, not 12. So it is very important word repeat, repetition. If you're not allowed to repeat, then you get this permutation. So no repetition. Do not repeat anything. I'm not going to write all that word. I have a hard time. So make it short. No repetition. No repeating. So maybe I'll stop at this stage, and on Wednesday we'll continue discussing this ideas of permutations and combinations. Those of you that took statistics, I think we'll also do this in MGF classes, permutations, combinations. So you'll probably be familiar with this. But turns out this is heavily used in mathematics and later stories. In fact, in section 12.5 that I'm going to probably talk about Friday or something, we'll see. So I don't give you a quiz on this. We'll stop at this stage and we'll enjoy this next time. So if you have any questions, I'm still waiting for